Okay, hi. We're going to do radians and degrees today, as well as we're going to stop into a little bit of arc length. So we've worked with degrees in high school for the most part. And the idea of degrees is we have a circle, and the circle can be broken up into partitions. Oh, that was terrible. Try again. Which partitions of little increments, in each of these increments are what we call a degree. Now, what a degree is, it isn't the measure of a length from a distance, from left to right. It is how much something is turning. And that's what a degree is, how much we've turned. So if I make a 90-degree turn, I go from going straight and I make a right turn. I make a 90-degree turn, and then I make a right turn, and then I make a right turn, and a right turn, and a right turn. So it is how much we're turning. If you hear people on skateboards, they did a 180. You do a 180 is because you flip your skateboard from one side all the way to the other. If you do a 360, you completed a full circle coming around to complete that turn. Now, there are pros and cons about degrees. One of the pros is that we're used to it. We talk about everything in degrees. This isn't like metric and imperial, where an inch and a centimeter are just depending on where you live. People in math and science use degrees and radians interchangeably, but there are some pros to each of these. First, when we casually talk about degrees, we understand that 360 is turning a full circle around. Please don't ever use the word 360 in context of, man, I used to be in a life of drugs, and then I made a 360-degree change, and I'm still on drugs. Because if you do a 360-degree change, you're back on the same course. I used to be an alcoholic, and then I did a 360. Sorry, it's a 180, right? So you did a 180-degree turn. And it's all about how much we are bending in a sense. I'm going in that direction, and I'm turning, and the measure of how much I turn is what we use degrees for. Now, just some math history, made up math history. Where do you think 360 degrees comes from? Because that's just really an abstract number. So let's see. I'm going to pause the recording and see if anyone has an answer. So someone mentioned the calendar. And in some customs, 360 was the number of days in a year. Because they weren't as accurate as us. For instance, a year for us is something like 360 and a quarter of a day. That's why every 4 years we have that leap year where we have that one extra day in February. So 360, if you observe, the sky and the calendar and the weather, you're like, hey, it's cold again. 360 days later, it's cold again. So that is what we refer to as the number of days it takes for us to rotate around the Earth. So you can imagine early mathematicians probably got 360 because of this idea of it takes 1 year, 360 days for us to go around the Earth. That's round, we're round, this is round. That's a way for us to come up with a definitive separation between our turns. And for us, I would say it's almost ingrained in our system, even in popular entertainment and media, that 360 is this idea of spinning around. A 180, making a 90-degree turn. Right? A right turn is a 90-degree turn. We also call a right angle similar to a right turn, right? Same idea of right. So where does radians step into place? Because radians describe exactly the same thing, but using a different set of terms. Now, instead of this abstract number of 360, imagine if a set of aliens one day came to Earth and we tried to say, oh, 360. 360 is a circle. Of course, that's math. They'd be like, what's 360? Unless if they've been stalking us for the last, year, they have no clue that it takes 360 days to 365 days. They're like, 360, 365. What's wrong with these people? They suck at math. They can't even count the number of days. So the idea of 360 is an abstract number that's applied to a circle. So when they decided to use radians, let's look at the word radians. There is a word here embedded in radians that gives you a hint what radians is related to. Thank you, radius. So if you look at the word radius here, you know radii, but this is it, radius. So for every circle, we know, for every circle, we know every circle has a radius, and our definition of a circle is all the points equal distant away from a center point. So any way you draw it, you always end up with a radius that's exactly the same distance for a full circle. Now, how are radians used? Well, the idea of a radian is, what if I took my radius here and I walked it, let's draw a different way. What if I took my radius, and in class I would have done this on a chalkboard, but I can't. So what if I took this radius and I laid it out almost like tile across the circumference of my circle? We would end up with 1, 2, 3, 4, 5, 6, and a little bit. And of course, if we were in class, I could demonstrate this a lot easier. But if I took my radius, and even if the radius was super big for a super big circle, that's a bigger R, right? This R would still take 1, 2, 3, 4, 5, 6, and a little bit. Even if I draw a little tiny circle with a little R, it would still be 1, 2, 3, 4, 5, 6, and a little bit. And turn out, it gives us our equation 2 pi. So radians count using how many radii, can go around a full circle. And it turns out the ratio is 2 pi. Or in degrees, or sorry, in decimal, that's 6.28 ... forever. It takes 2 radius. Now, we don't really talk about radius. We usually use this formula. The circumference of a circle is 2 pi r. Oops, sorry. 2 pi r. Or a circumference is also pi d. Now, another way of looking at this is talking about using diameter. If I took any circle and I drew a line between one point across the center to the other, this is the diameter. So how many diameters fit across the circumference of the circle? If I start at the top and I laid my first diameter, it would look about something like this. So that's 1 diameter. Then we would have 2 diameters, and then 3 diameters, and it'd be 3.14 diameters. It turns out it takes us 1, 2, 3.14. And that's where the number pi comes from. Early civilizations realized that for all circles, no matter how big or how small, the only actual thing you can draw inside a circle is a diameter. See, this diameter is the only point. If I draw any other 2 points randomly between any 2 parts of a circle, they could always change, but the diameter would always remain the same throughout any circle. So how many diameters go around a circle? 3.14. So the idea of radians are formed using this formula. It's the arc divided by the radius. This is the arc of your circle divided by the radius of the circle. Or another way of thinking about it, how many radiuses are in the arc? Now, if we think of a dumb example, what is the circumference of a full circle? What is the distance around a full circle? We said our equation for a full circle was 2 pi, whoops. Our equation was 2 pi r. If we divide that by radius, this will give us the radians definition. And if you notice, there's something interesting about this formula. No matter what, the r's always divide out. When the r's divide out, we are left with a radius of, or radians of 2 pi. To go around a full circle, any size circle, it is always going to be 2 pi. If I give you a circle with a radius of 3, means a diameter of 6. The circumference of the circle is 2 pi r, which is 2 pi 3, which is 6 pi. How many radians does the circle take to go all the way around? The radians, which is a measure of turn. If I want to start here and I want to turn all the way around, it's going to be 6 pi over r, the radius, which gives us 2 pi. Now, I'm going to give you guys some special radian marks. I'm going to do some special radian marks, and let's draw our full circle again. So, draw a line across. We'll call this 0 and 2 pi. And 2 pi is synonymous with 360 degrees. What is half of 360? What is half of 360? We know that is 180. What is half of 2 pi? Half of 2 pi, 2 pi divided by 2 is just pi. So if I want to say in radians, pi is the same as degrees 180. But it wouldn't sound as catchy if I said, oh, I made a change in my life. I made a pi turn. You turn to pi? What type of pie? Apple pie? Did you add ice cream to it? Is it a la mode? So this idea of pi is half a circle if we're counting in radians. Let's cut this in half again. What is half of 180? That's 90 degrees. And half of pi is just pi over 2. Let's cut this in half again. What's half of 90 degrees? That's 45 degrees. I should put a little degree mark on the corner to denote its degrees. And here's a hint, pi over 2 over 2. What's half of 50 cents? Half of 50 cents is a quarter. But if we do it algebraically, we don't like dividing fractions, we multiply by the reciprocal instead, which is pi over 4. Okay, so let's start counting. We're going to be counting by these main increments. So I want to break up the circle into quarters. Pi over 4, quarter pies. So if I say this is 1/4, right here, wouldn't this be considered, wouldn't this be considered 2/4 then? A quarter plus a quarter is 2/4. 2/4, 2 pi over 4. Isn't that just pi over 2? Okay, a quarter plus a quarter. Let's add another quarter here. So we're looking at 1/4, 2, sorry, whoops, wrote that wrong. 1/4, you don't need to copy this part. 2/4, and this is 3/4. Are you guys okay with me saying 1, 2, 3 quarters? Right? And now, this is where people are confused. Doesn't this look like, how come you're saying this is a quarter? Isn't this picture a quarter? Are we talking about a quarter of a circle? And what happens is people get confused because this whole circle is not pi. This whole circle is actually 2 pi. Pi is right here. So if I say this here is pi, only the top half of it, then a quarter really is that much. Okay, so quarter is really 1/8 of the full circle, quarter pi. So let's go ahead and I want to rewrite this. I want to walk ourselves across. So this is now 3 pi over 4. I cannot reduce. Over here is going to be 4, oops, wrong color, colorblind. 4 pi over 4, which becomes pi. It reduces down to pi. If we keep on going, 1, 2, 3, 4, This is going to be 5 pi over 4. We cannot reduce. Over here is going to be 6 pi over 4. Can I reduce 6 and 4? That becomes 3 pi over 2. One more break. 1, 2, 3, 4, 5, 6. Right? We did 1, 2, 3, 4, 5, 6. Now we're on 7. 7 pi over 4. Oops. 7 pi over 4. And then we're done with 8 pi over 4. Once we're at 8 pi over 4, that reduces down to 2 pi. So these are equivalent statements for us. Whether we use degrees or radians, they're pretty much the same thing. The point of it is, why do we have to use two different, and why do we have two different systems? Is because one is based on the abstract, you could say 360 degrees. That only works on Earth. While the other one is based on itself. It's based on radians. It's based on the radius. So that no matter what culture we're from, no matter what universe we're from, we can all say, hey, the radius is going to be the same no matter what planet you're from, and we can talk in a common language. I'm going to go ahead and fill out the rest of the radians here. 45 plus 45 is 90. 90 plus 45 is 135 degrees. Keep on going. 135 plus 45, that is 170 plus 10 is 180. So 180. 180 plus 40. Here's, 45. Here's a gimmick. Don't add the 5. When you're doing math quickly, don't add the 5. What is 18 plus 4? 18, 19, 20, 21, 22. Right? So this is, if I'm adding 40 to it, is 225. 225 plus 45. Add another 4. 22, 23, 24, 25, 26. Add 10 is 270 degrees. 27, 28, 29, 30, 31, 31. Add a 5. 31, 32, 33, 34, 35. Add a 10, and we're at 360. So for us, we have two unit circles that we have to make sure we know. One is that the unit circle created from degrees, and one unit circle created from radians. Now, this is literally, unfortunately, only half the ways that we're going to cut it. We've cut it by quarters and by halves. Now we're going to cut it by thirds and sixths. Thirds and sixths. So let's draw our next circle here. Okay. Our next circle in your notes, draw another circle. Oh gosh. Oh, it's terrible. Come on. Did this so much better on the chalkboard. Okay. Draw my line across to make it easy. And I'm going to write 180 here. Let's use in red. Yes, let's see. So 180 in red and 360 in red. And we got 2 pi, 2 pi, and pi. Now we're going to cut this in a different way. We're going to cut this in 30-degree marks. But instead of 30, let's do a bigger one. Let's do 60. So how many times does 60 go into 180? 180 divided by 60 is 3. So this becomes a third. Go ahead and continue the lines to the other side. And we're going to be counting by 60 degrees.
Wait, Mr. Crow.
Yes, give me a sec.
Oh,
1 second, please. So we're going to break this up into 60 degrees. We have 60, 60 plus 60. If this is 60 and this is 60, we add them together. We end up with 120. 120 plus 60 leads us to 180. Oh, darn it. Let me rewrite this using red. 60, 120, Don't forget the little degree mark. Now let's forget it. Then we have 180 plus 60 is 240. 240 plus 60 is 300. Now, if you haven't caught on yet, these are pretty much your multiplication tables by 6. 6 times 2 is 12. 6 times 3 is 18. 6 times 4 is 24. 6 times 5 is 30. 6 times 6 is 36, okay? So just in case you need that. Let's write this in radians. So if you remember right here, we said pi divided by 60. Now instead, we're gonna look at this, pi divided by 3, which is gonna give us the equivalent 60 degrees. So there's gonna be pi over 3. This is 1/3 of pi. 1/3 plus 1/3 is 2/3. 2 pi over 3. This would be 3 pi over 3. And those divide out nicely and cleanly. Those divide out. We have 4 pi over 3, 5 pi over 3, and then our last one, 6 pi over 3, 6 pi over 3, which leads us back to 2 pi. Again, if you think of pi as 180, if you can go back and forth in your brain and think of pi as 180. If pi is 180 degrees, then if we divide both sides by 3, pi over 3 is equivalent to the same as 60 degrees. So we're gonna cut this up one more time to become a finer degree, and that's going to be 30 degrees. So I'm gonna draw this in half. So take a look here. I'm just gonna cut this in half. And that's gonna be 30 degrees for us. So what is half of pi over 3? Now, here's a gimmick if you guys don't know. Whenever you're dividing anything by 2, you just multiply the denominator by 2. If I say, so let me say this again, pi over 3 divided by 2 is the same as just multiplying the bottom number by 2, pi over 6. Whenever you're dividing anything in half, it's the same thing as just multiply the denominator by 2. Here's a dumb one on the side. If I say 5 over 7, what is half of 5 over 7? It's just 5 over 14. That's half of it. Please just multiply the denominator by 2. FYI, okay? So we're going to start counting. This is pi over 6 because we cut pi over 3 in half. That's our counting. This is pi over 6. Sorry, trying to get this out, but it doesn't want to come out. Okay, this is pi over 6. The next step here would be 2 pi over 6. And doesn't 2 pi over 6 reduce to pi over 3? Yeah, we're totally overlapping. If I take the next step, cutting this in half, this is 3 pi over 6, 3 pi over 6, but doesn't 3 and 6 reduce? Yes, it does, and it goes back to pi over 2, which is the same as 90 degrees. 30 plus 30 is 60, 60 plus 30 is 90, 90 plus 30 is 120. So all these fractions line up. So they, in essence, will start overlapping. This is 4 pi over 6. 4 pi over 6, which still reduces down to 2 pi over 3. This would be 5 pi over 6. Moving over is 6 pi over 6, which reduces to pi. Next one is after 6 is 7 pi over 6. 8 pi over 6, 9 pi over 6, which reduces, let me rewrite that, 9 pi over 6 reduces to 3 pi over 2, which is exactly what we wrote over here on the left. 9, 10, 10 pi over 6 reduces to 5 pi over 3. And the last one is 10, 11, wait, one more. 11 pi, whoops, those are really too close together. Let me rewrite those. The next one is, to reset, too close. Is 11 pi over 6. And this is going to be 12 pi over 6, which reduces to 2 pi. Okay, so this is fine and dandy. And your goal is to memorize these two charts. You have to memorize these two charts because you have to be able to convert from radians to degrees really quickly. And these are the most popular radians degrees that we will be using. 30, 60, 90, 30, 60, 90, 45 degrees. These are the most popular ones. And even in calculus, you'll be asked to know your sine, cosine, tangent of each of these angles without taking a calculator out. So let's do one more thing here. And this next thing is this. Converting from degrees to radians and vice versa and back. Okay, our goal is to go from degrees to radians and radians to degrees and back and forth. Now here is the easy one. So if I have 180 degrees, how could I convert this to pi? And didn't we say 180 and pi are exactly the same thing? And if you remember from Algebra 1, when you do conversions from feet to inches, or from, what else do you guys do? Feet to inches, from feet to yards, there's ways of writing a fraction to get that to work. And that's what we're gonna do. So here's the key. If I'm changing from degrees to radians, we're gonna use this identity. From degrees to radians, you are gonna use 180, sorry, whoops, all the way around. Pi over 180. If you're gonna go from radians to degrees, you will use 180 over pi. And I'll show you guys how to use it right now. And a way to remember it. So I want radians. I have degrees. You state what you want. I want radians on top. What do you have to cancel out? Degrees. The math works out. Done. Let's try this again using a different angle. 90 degrees. Okay? I want radians. I have degrees. Okay, so how do I go from degrees to radians? Remember, I want radians. I write radians on top. If I want to have radians, I need to get rid of degrees. Well, what's the equivalent statement to 180 radians? It's 180, to 1 radian, it's 180 degrees. 90 and 180 cancel out, they reduce. And we're left with a 2 on the bottom. So it's pi over 2. And that's right, pi over 2 is 90 degrees. 60 degrees. How do I change this to radians? I want radians. I write radians at the top. I want to get rid of degrees. 180 and 6, they divide out into 3. Pi over 3. So does this work with all types of numbers? Yeah. So even if you have something, let's say 50 degrees, 50 degrees, I have degrees, I want radians. Divide by 180, this becomes pi over, well, 5 pi over 18. You're done. No more reducing. This is your answer. If you want to go backwards, let's go from radians to degrees. Okay, I have pi over 4 radians, and I want to change this to degrees. So you state what you want. I want degrees, right? I want degrees. So I write degrees on top. So it's not always one or the other on the top or the bottom. It's all about what do you want to convert this to. I want degrees, so I put 180 on top. So we have to put pi on the bottom. Okay, the pi's divide out. See, I cancel out my radians. So we're left with 180 divided by 4. So in my mind, I can't do that, but I could divide it by 2. What's 180 divided by 2? 90. Half of 90 is 45. If you look at the chart, pi over 4 is 45 degrees. Let's draw this. If this is pi, and we divide this into 4 sections, 45 degrees would be pi over 4. 180, 90, 45. Equivalent. Let's do another one. Let's do pi over 6. I want degrees. So I write degrees on top. And I have to say, what is this equivalent to? This is equivalent to pi. The pi's go away. And 180 divided by 6, 18 divided by 6 is 3. Add a 0, 30 degrees. Okay. How are we doing? Fairly simple? Okay. I want to say one more thing. Okay. Let's spend the last 5 minutes on this last part. Okay. So whenever we're converting, we can, one, straight memorize it and know it already. Straight memorize it so we know what the fast conversion is. You guys will be responsible for learning both these 2 circles, converting 30 degrees, 60, 45, and 90. These are the main ones. That's it. I don't care about 43 degrees. I don't care about 13 degrees. Only 30, 60, 90, and 45. The next part is converting using algebra, an algebraic way, using the fractions. You always write what you want on top. Write what you want on top. If I want radians, write radians on top. If you want degrees, like here, I want degrees. So I wrote degrees on top. And the last one is, we're going to do radians to arcs. Arc length. We mentioned before that what are radians? Radians is just the radius. So if I give you 3, sorry, that's the easy one. If I give you pi, that's my radians. And I want to convert this to how much of the circle would pi take up? Isn't pi over here? So what is the arc length? Which is this highlighted section here. This is the arc length. It's another way of saying like circumference, but not the full circle, just as much as you want. So if I turn pi, how much of the arc would I have traveled? Now, the formula for this is, I think an easy way of saying it, but it's really theta is equal to S over r. Theta, which is our radians, is equal to the arc divided by the radius. And if you remember, we've actually saw this equation up at the top because radians is just the radius divided by how much of the circle you're looking at. Again, it's the radius divided by how much the circle you're looking at. So on your homework today, you guys are going to be doing that. You're going to convert from a radian that they're going to give you, and they're going to give you the radius, and you're going to have to convert that to some type of arc length. So if I tell you, let's look at some examples. If my radius, theta, is equal to pi, and my radius is equal to 1, we're just going to plug these values into this equation here. So pi is equal to s over 1, okay? As simple as plugging it into the equation. Solve for s. S is equal to pi. That's it. That's actually the length. Now, what we're describing here is if my radius, the distance from here to here, was 1, r is equal to 1. But what if this was bigger? Let me give me 1 second. Theta is equal to pi. What if r was equal to 3? So wouldn't my circle be even bigger? Same formula. Pi is equal to s over r. That means the length of my sector, multiply 3 to both sides, s would now be 3 pi. It would be larger. If theta was pi over 4, just a quarter of a circle, and my radius was 4, let's say, okay? I'm going to tie this around, and I'll show you this actually works. The formula is theta is equal to s over r. So I want to draw the circle over here on my right. The radius is 4. And the angle here is going to look like pi over 4. Pi over 4 is right here. That's my angle, pi over 4. So how much would this sector be, okay, of the circle? Well, that's just use the formula. Let's not overthink it. It's going to be pi over 4 is equal to s over r, which is 4. We're going to multiply 4 to both sides. S is equal to 4 pi over 2, which reduces to 2 pi. 2 pi doesn't look like the right answer, but is it? I'm going to show you another way of looking at it. If my radius was 4, what is the full length of the circle? What is the full circumference of the circle? The circumference here is 2 pi r. The circumference is 2 pi times 4. So we're saying the full circle is 8 pi. If the full circle is 8 pi, wouldn't you say half of it is 4 pi? Wouldn't you say half of that is, whoops, what did I mess up? I made the mistake right here. This is not a 2. This was a 4, right? Shoot. Okay, let me fix that. This was actually a 4. Everyone take a look. This was actually a 4. So that means this is a 4. It's a 4 here. And this here would be a 1. So let's go ahead and do what we said before. We said the full circle is 8 pi. Half of this circle would take me back to 4 pi. Half of that would be 2 pi. And half of this, to get a 45-degree angle, would be pi. So the length here would be pi, which matches what we came up algebraically. Okay. Now, if this was any other value, you could, again, just follow our steps, solving for the missing side. a missing variable, and you could also then find our arc length.